Today, we're going to do two tutorials. One will be focusing on contrapositive and contradiction, and the other one, so you'll see that it's tutorial 5, which is the first 2 pages. You can see it on Discord. So Discord here, go to the tutorial worksheet. This link will give you this channel, and you go open tutorial 5 and 6. Okay, we'll do both today because we don't have another tutorial before your midterm, so I plan to do both of them in one tutorial. So we'll do 5 and 6. And you should know that both are extremely important, that I think they will both be tested. So okay, that's my opinion, that you'll get one question on either contrapositive or contradiction, and another question on induction. That's my guess. So, or even 2 questions on the first one. It happens. But anyway, so those 2 are extremely important, and I'm telling you, you should practice a lot. I will send you practice questions from before that I made. Those are open to public on my YouTube channel as well. But please make sure you use the reading week to study for the test. Anyway, so let me just get started. First, I'm going to talk about contrapositive. And contrapositive is for if-then statements. So when you see if-then statement, that means you might want to use proof by contrapositive. So when you might ask me, well, when do I use contrapositive? When do I use contradiction? Contrapositive only works for if-then statement. Okay, it has to be P implies Q. Nothing else. So some keywords will be, well, let's write it down. Contrapositive. One is, it's definitely if then. So I'm telling you purely if, and something you have, like, for example, not equal, and then something also not equal. If you see something like this, then well maybe you want to use contrapositive. So using contrapositive, you have if something equal to something, then something equal to something, which is easier than inequality. So if you have something like this, it's a strong sign for you to use contrapositive. Another one I always say is, okay, let's say if then statement. That is, if you have a complicated expression, and then you have them. Okay, they asked you to prove, and what is here is something very simple. If you have something like this, that's another strong sign that you need to use contrapositive. Why? Because starting with something simple or reach something complicated is a lot easier. Okay, it's a lot easier. So what do I mean by complicated expression? For example, this. You can see that proof that if a long or big expression is odd, then both x and y are odd. The fact that you know x or y, those are simple things, right? Those are simple things. So this is a very classic or typical contrapositive question. If you look at example 2 here, you'll see that it's the same thing. Here, it's something complicated, but what you need to prove here is something very simple. So again, this is a classic or a typical contrapositive question. They even look like you need to use contrapositive for them. Does that make sense for everyone? For both contrapositive and contradiction in this course, in this specific course, they really like to test you on something even odd, even. Those kind of questions are the professor's favorite. Okay, so whenever, let's say you go to your textbook, you go to this chapter, and you wonder which questions are more important than the other. If they have even odd, you do them. Okay, you do all of them. That's my suggestion. Okay, so let's look at example 1. X, y are integers. Prove that if x, y squared minus 2x squared, y is odd, then both x and y are odd. Before we start the proof, I'm asking all of you to always write down what the contrapositive is. So always start with what the contrapositive is. Because if you, let's say, suppose you don't know how to prove it, or suppose your proof is completely wrong, just having the correct contrapositive will give you a mark. This question, let's say it's out of 4, then having a correct contrapositive will be 1 mark. So you want to make sure you get this 1 mark. Okay? However, this 1 mark sometimes it's not easy to get because people make a mistake. And here I can tell you, if you use proof by contrapositive and your contrapositive is wrong, you will get 0. Okay, you'll get 0 out of 4. The TA will not read the rest of your solution. They look at the first line, it's a wrong contrapositive, they give you 0. And even if you request remark, I'm not going to give you more marks back. So you make sure your contrapositive is indeed correct. P implies Q, contrapositive is not Q, implies not P. This is the first mistake people make. So this part, a lot of people will get it wrong already. And I'm telling you, this question people will get it wrong again. Even with this writing here, it's written down right here, a lot of people will get it wrong. So let's see. What do you guys think? What is the contrapositive of this statement? Anyone? If x or y is even, then expression is even. That is correct. That is correct. That's nice. Nice. That's correct. Okay. Let's start with let's prove it's contrapositive. So what is a contrapositive? If x keyword is or, y is even, then xy squared minus 2x squared y is even. Okay, so a few mistakes people usually make. One is they get this part wrong. The other one I want to mention is people get this part wrong. Originally, you have and statement, right? Originally, you have and statement. When you negate it, you change it to or. Okay, this is a common mistake. And here, I think it's quite obvious you have an and statement. What I want to say is sometimes it's not that obvious, and I want to emphasize this. Okay, so here, a common mistake. What is a negation of x is in between 1 and, let's say, 3? How do I negate this? This is a common mistake. Okay? If I want you to prove this, the negation of this, how do you negate it? Anyone want to give it a try? What is the negation of x is in between 1 and 3? X is greater than 1 or x is greater than or equal to 3. That's correct. That's correct. Continue. Okay, that's great. Okay, so this is what I want to say. This is also an and statement, okay? Because x has to be greater than or equal to 1 and smaller than 3. So this is actually an and statement. If you negate it, you need to negate it to be an or statement. So that's going to be x is greater than 1. So we'll be doing this. Or x is small. Sorry. What am I talking? X is smaller than 1. X is smaller than 1. Or x is greater than or equal to 3. Okay, so there are a few traps here. One is this is an and statement. Second is, well, even if you just negate this, what is the negation of that? The opposite of greater than or equal to is smaller than. The opposite of smaller than is greater than or equal to. Okay, so there are several traps I set for you, and good that now you jumped in, but this is the most common mistake people make. Okay, so if you see this, just need to remind yourself this is an and statement and you need to negate it, you need to put or there. So now let's come back to this. If x or y is even, then xy squared minus 2x squared y is even. So let's make our assumption. Suppose x is even. Okay, if x is even, I can write it x as, let's say, 2k, where k is an integer. Here is the other mistake, okay? So this part, a lot of people would forget about it. If you want to say it's an even number, you need to make sure it's a multiple of 2. Multiple 2 means 2 times an integer, not just any real number. It has to be an integer. So you cannot forget about this part. Okay, so now I can plug it back in. So then xy square minus 2x square y equals to 2k y square minus 2 times 2k square y, which you can factor out to here. So if you want to show something is even, you always write it as 2 times an integer. Okay, so I want to factor out a 2 here. That's going to be 2 times, the first term is left with 2k squared, y squared minus 2k whole thing squared y. Okay, which is even. This is when x is even. Okay, this is when x is even. In this case, I did not care what y is. I use the same y. So y is just any integer. I don't care if it's even or odd at the moment because, well, what's if x or y? Okay, so in another case, I have to discuss y as well. So now suppose y is even. Then again, we can write it as 2 times the integer. Let's say 2l, where l is the integer. Then the whole expression is gonna be different again. So that's gonna be x times 2l whole thing squared minus 2x squared 2l. Again, factor out 2, I'll be left with 2x squared l squared minus 2l x squared, which is even again. Okay, so we can see that in this case, I only need to discuss 2 cases, x is even or y is even. I only need to discuss 2 because, well, when x is even, I did not care y. Okay, I did not set y to be even or odd. If you want to set both, then you'd have more than 2 cases to discuss. Okay, if you want to say both, so let me write down. Let's say if you want to set up both, then you have 3 cases to talk about. So you can also do case 1, x, y are both even. Case 2, x is even, y is odd. In case 3, x is odd, y is even. Which also works, but it's a lot longer than what I have here. Okay? It also works. It's not like, oh, I cannot do that. It also works. Okay? Does this make sense to everyone? Why do I only need 2 cases here? This good? Yeah? Can we also just say, oh, that's what I just did. We don't need to pick those in order to prove the implication. What do you mean check those 3 cases? If you set both like this, like both x and y, then you need to check 3 cases. Okay? If you don't set up both for each of the cases, then you only have 2 cases. So like x is even, where y can be anything, or y is even, where x can be anything. Yes, that's correct. So it really is up to you. Yes, that's correct. Either the black one or the orange one, it's up to you. But I want to say is if you choose to do the orange one, you have to discuss all 3 cases. Make sense? Okay, here is a question for you guys. I know that some of you know without loss of generality. Can we use it here? Can I say log or less without loss of generality? Suppose x is even. What do you think? Would it work here? Should I erase it or I'll talk about that later. Okay, we're not done yet. We're not done with the question yet. But my question is, what do you guys think? Does log work here? What do you think? Or symmetry work here? Whichever one you know. Can I say without loss of generality, suppose x is even? What do you guys think? Oh, I don't think you understand without loss of generality. Okay, if you don't know what it is, you can forget about my question. Okay, I'm asking the people who know what it is. So with log, for some of the question, with log, you don't need to talk about all the cases. Okay, so I'm asking you, can I use log here and only talk about one case, whereas x is even or y is even, but only talk about one of them, not both of them? Do you think it would work? That's correct. So even if I'd only do one case, it would work. The answer is no. Okay, you cannot use log here. You cannot. Why? Why? Because x and y, they are not symmetric. Okay? They are not symmetric. The first part here, it doesn't matter if you switch x or y. But here it matters. Do you guys see it? Right here it matters. Okay? Even if I switch x or y, it will be different. Okay? Unless I have like if I remove this 2 here, then you can use block. Does that make sense? But in this case, they are not symmetric, so you should not use block here. You should discuss the 2 different cases. We never discussed them, but I know a lot of people use them, so just making sure that people who want to use them are using it correctly. If you don't know what it is, then just don't worry about it. Okay. Yes. So once we get here, you should make a conclusion. Okay. So you should have a conclusion sentence. You should say, well, since the contrapositive is logically equivalent to original statement, the original statement is also true. Okay. And you can call it the end of the proof. Are we clear? Clear? Guys, clear? Yes, okay. I hope you do not make those mistakes, okay? Let's give example 3 a try. So let's do contradiction directly because I have like 20 minutes left. Let's do contradiction. Okay, it's quite important. So proof by contradiction is quite similar to proof by contrapositive. You still can have if-then statement, but it doesn't always work for if-then statements. It can work for anything. But the key here is you suppose the negation. So you assume the negation. So if you have an if-then statement, then your assumption will be both P and negation Q are true because, well, that's a negation of P implies Q, right? The negation of this. Remember, the negation of this is P and not Q. And I said assume the negation, which means we assume this if you have P implies Q. Okay? That's not always the case. Sometimes you just have something like, so let me say contradiction. You sometimes just have something like, oh, there is no something. There is no solution. Something like that. Okay, that's a classic contradiction question. They say no, so you assume yes. They said there is no solution, or there is no rational solution, there is no integer solution. If you have something like that, you suppose, well, there is solution, there is integer solution, there is rational solution, and so on. That's a classic contradiction question. Another one is prove something is empty. Okay, if you want to prove something is empty, it's not that easy. Okay, it's not that easy. So suppose it's not empty, it's a lot easier to deal with because once you suppose it's not empty, you can always pick an element from it. Because remember, for set question, we always deal with elements in there, not set directly. So if they ask you to prove something is empty, well, you really suppose it's not, and then, well, since it's not empty, there must be at least one element in there, and you can deal with this element instead of dealing with the whole set. So prove something is empty is another classic contradiction question. Something else will be prove something is infinite, or infinitely many solutions, infinitely many primes, something like that. Okay, why do we use contradiction? Because, well, infinity is hard to deal with. But if you suppose the opposite, which is finite, that's a lot easier to deal with. Okay, so contradiction is usually used when you have something hard to prove. So you suppose not, because if you suppose not, it might change your problem to an easier problem. That's why we use contradiction. Okay, so infinite is another keyword which you might not see a lot in this course, but in the future math courses you might be able to see them quite often. And you remember I told you that those are good contradiction questions. So maybe you want to try contradiction. Okay, so those are classic contradiction questions. And I also want to talk about one thing is what is the difference between contradiction and contrapositive? They both works for a if-then statement, but for contrapositive, so if you have an if-then statement, right? For contrapositive, your assumption is not Q. For contradiction, your assumption is not just not Q, it's P and not Q. Okay, you have an extra term here. Do you guys see it? So if the question asks you to use contrapositive, you cannot use contradiction. And if they ask you to use contradiction, you are not supposed to use contrapositive or direct proof. Use what the question asks you to do. If they don't tell you, then you need to decide which one you want to do. And I already told you how to determine that. I gave you some classic examples. Okay, so is everything clear so far? Before we move on to example. Cool. Let's see. Is everything clear? Are we good? Yeah? Yeah? Okay, cool. Let's try this. I think I'll give you, let's say 2 minutes to give it a try because I just talked about how to do it. If you don't remember, I said it here. Okay? I briefly talked about how to approach it, so give it a try and we'll do it together. Okay, what do you guys think? What's my assumption? Guys, what's my assumption? You're gonna make sure your assumption is correct, so what is my assumption? Nobody wants to say? Disjoint thing? Okay, and anything else? So let me write it down. For contradiction. Suppose. Okay, let's see. A cross B and C cross D are disjoint, and A intersect C is not empty. Ooh, and sorry, then B intersect D is not empty. If A cross B and C cross D are disjoint, then not the rest. Notion, no, that's not correct. Look ahead, look above us. What did I say? We need to look. So the first part and A and C are not empty, and B and D are not empty. That is correct. That is correct. Okay, nice. Okay, so let me write it down. For contradiction, suppose a Cartesian product B and C Cartesian product D are disjoint, and I'm just gonna just say that they are disjoint. A intersect C, not empty, and B intersect D is not empty. Okay, so this is what we do. We suppose the negation of the original statement and the C negation. And as I mentioned before, when you have this kind of thing, we start with, well, they're not empty. That means, well, there must be something in there, right? So let's let, I know not empty, so X is any element that's inside of this intersection. Y is another element that's inside this intersection, right? Because they're not empty, I know something must be in there, and let X be an element that's in there, Y be an element that's in another thing. You cannot, okay, by the way, you cannot use X again here, okay? You cannot do that because we do not know if X is involved. So you have to pick a different element. Now, by definition of intersection, I have X is in A and X is in C, Y is in B, and Y is in D. Okay? And what do we do now? What is my contradiction here? I need to reach a contradiction. What is it? What do you think? So what is my contradiction? If I have this, what's gonna go wrong? We're almost there. X and Y belong to both. That is correct. That is correct. There is an element that is in the Cartesian product. Alright, so we need to write it down. Okay, so now by definition of Cartesian product, I have X is in A. Sorry, because I want to use X Y is in A, Cartesian product B. Because why? Because X is in A, Y is in B. We highlighted X is in A, Y is in B. That's gonna give me X, Y is in A intercept B. And similarly, X is in C, Y is in D. It's gonna give me and X, Y is also in C, Cartesian product B. How do we get this? We get it from the highlighted part. Means X, Y is in a Cartesian product B intersect C Cartesian product D. Because this element is in both of them. Okay, that means well, it's in the intersection, which contradicts. But before we said they're disjoint. Oops, which contradicts with them being disjoint. Oh. Okay, so our assumption says they're disjoint, which means there should not be any element that are in both. However, I found an element that's in both. So that's my contradiction. Okay, and you can see that without doing contradiction, this is not an easy statement to prove. Because there's not much you can do, because well, them being disjoint, there's no information you can get. Okay, I mean there is, you can just say, well, there is no and in A cross B, and in C cross D, but not in, it's harder to deal with than in. Okay, so is this question clear? Is clear? Clear? Yeah. Any question at all? Okay, let's move on. Example 4. This is the most classic question in this course. Okay, which means you have to know how to do it. And I say this every semester. What do I say? The proof itself is, the question itself is not that important. Why? Because it's very unlikely we'll give you the exact same question. Very, very unlikely. However, the proof itself, what can you learn from it, is what's important. And I've been repeating myself every week that you learn from the question you do, not memorizing the proof, not pray for the same question show up on the quiz or a test. You learn from what you did, and you can use the same technique on something else. So for this question, I'm gonna tell you what you can learn from this proof, and hopefully you remember what I said, and hopefully in the future you can apply them to some other questions. So I believe you guys did one like this in lecture. Did you? Did you guys do one like this in lecture? Is the original statement true or false? The original statement is true. When we ask you to prove something, you already know the original is gonna be a true statement. Okay, the original is true. You are 15 minutes behind in lecture. What do you mean? Oh yeah, I'm confused. You guys didn't cover this? No, you guys covered that last week, I remember. I remember him doing this. What do you mean? I was there last Thursday, isn't it? Yeah, I was in that class last Thursday and he did this one. Okay, so I suppose most of you are familiar with the proof already. In that case, I'm not going to give you time to work on it. What I really want to talk about is, well, I'll do the proof, yes, but what I really want to talk about is what you can learn from the proof. Okay, so let's quickly start. See, okay, let's quickly start. Well, classic contradiction question, because there is a no here. right? Before I said we have something something, no something something, contradiction. Okay, so they said no rational number is x such that x plus x cubed equals to 1. Since they said no, we suppose yes. So for contradiction, suppose there is x that's irrational such that x plus x cubed equals to 1. That's our assumption. And here comes the first thing you learn. Okay, the first thing, important thing you learn is whenever you suppose something like this, whenever you have this, we can rewrite x. As following. Okay, the red part is not part of the proof. It's something I want to emphasize. Okay, so we can write x as p over q, for example, where p, q are both integer. Q cannot be 0, and p, q are relatively prime. What's relatively prime means that they don't have common divisors other than 1. Okay, so the other way to write it is GCD of PQ equals to 1. Or you can say P over Q is in its lowest term. Either way works, okay? You can either say they're relatively prime, or GCD is 1, or it's in the lowest term. Either way works. They all mean the same thing. But what I want to say is, when you have this, you can always write this, okay? Do not forget about any condition. A lot of people will forget about this part. A lot of people will forget about this part. Do not forget about those conditions. You will see such things again in chapter 6. Okay? In chapter 6, I'm literally gonna come back and tell you I told you so. I'm telling you right now, okay? So whenever you have an element that's rational, you can do this. Okay? You can say, this is the same as P over Q, where P, Q are integers, Q is not 0, P and Q are relatively prime. Any questions so far? No? I suppose not. If you have any question, please just type in the chat. I'll check regularly. Now, since I have this, I can plug it back into this equation. So let's do that. Now we're gonna have P over Q plus P over QQ equals to 1. Okay, this is after I sub in my x, which is P over Q, back into the equation. That's the second thing you can do here. Okay, so the second thing here is we, if possible, we prefer integers over rationals. What does that mean? It means that, if possible, I want to turn this whole thing into an equation of integers instead of an equation of rationals or fractions. Okay, so here is what I'm saying is turn into an equation of integers. Okay, so because I want to deal with integers instead of rationals, I'm gonna try to multiply by q cubed on both sides of the equation. That's gonna give me pq squared plus p cubed equals to q cubed. This makes sense to everyone right now. Why am I doing this? Because we prefer integers over rationals. Okay? Question so far? That's the first or the second thing you learn. Yes, that's correct. Yeah, that's correct. How are we gonna get channel? Oh, I'll give access to everyone. We do this to remove the repeats. That's why we're doing this. We do this to remove the repeats because, well, 1 over 2 and 2 over 4 or like 3 over 6, they're all the same thing. They all mean the same number. So instead of having all of them, I remove all the repeated ones and I leave with only one. So for each value of a number, we leave only one form of it. Does that make sense? We're just removing the repeats. If it's repeated, we remove it. So every element is unique. Make sense? That's what it means by lowest term or relatively prime. Otherwise, you'll just have lots of repeats. You have infinitely many of those. Okay. Now, this is the third thing we learned from this proof. That is, if we have an equation, or let's say if we have a sum or difference, sorry, sum or difference or product of integers. Okay, I did not say division, like okay. Why? Because that you might not have integers anymore. Those three operations will still give you integer, but if you divide, then you might not have integers anymore. That's why I am not mentioning it. Okay, that is why. If we have those, the following few techniques are very useful. Okay, I'll tell you all of them. One, the first one that I always check is even odd. What do I mean by that? Is you check, is this side even? If this is even, then this side should also be even. Okay, that's what you need to do. Check if the matches with even odd, if their parities are the same. If you got the same parity or they both are even or both are odd, there is no contradiction, then what I really check is something related to prime. Okay, prime, I would say prime factorization. What do I mean by that? It means that well, if you have equation, then this side and this side should be the same number, and the same number should have the same prime factorization. So for example, this side is 2 times 3 times 5. Then this side should also be 2 times 3 times 5, which means well 5 should be one of the divisor, 2 should be one of the divisor, 3 should be one of the divisor. If only one side has the divisor, or let's say prime factorization or divisors. Okay. Actually, divisor I'll talk about a separate. Prime factorization. So you should know that well, they should have the same prime factorization. Otherwise, it's not the same number. So that's your contradiction. 3 is divisor. So I'll talk about them separately. Divisors. So again, because it's an equality, they should have the same divisors. And in this course, what we usually use is division algorithm. This is chapter 6. To be honest, this is also chapter 6. So what would you guys do? Are you read this one instead, okay? Or some basic definitions. 1, 2, 3, 4 is check. Which is also divisor to be honest, part of it. Maybe I'll add it too. You know what? I'm gonna move this to the next line and add it. So 3 divisors, or division algorithm, or modular arithmetic. But again, this is later in the course as well. So in this chapter, we mainly focus on even odd. So almost always work. Okay, even odd in this chapter is what we use the most. We check the parity of the both sides. In other words, well, we need to discuss cases. So how many cases do we need to discuss, guys, in this case? Is it necessary to state this or work without? What is this? What is this then talking about? Stay what? As I said, the red ones are not part of the proof. Okay, the black ones are. 3. Why 3? Which 3? Really them. You should discuss both odd Yes, you have to state it because that can give you one of the contradiction. Both odd, both even, p even, q odd, p odd, q even. You need 4 cases. Okay, I'm not gonna do all 4 because, well, as always, I'll give you a solution. So, not all 4. I will talk about first 2. Okay, I'll do first 2. Which will give you the answer for one of your questions. Both odd. Okay. This course allow you to say something like all times odd is odd. Okay. If they're both odd, then from here, if they're both odd, then PQ square is it odd or even, guys? If they're both odd, if P and Q are both odd, is PQ square even or odd? Odd, that's correct. So this will be odd. What about PQ? Is it even or odd? If you don't know the answer, by the way, you can just think about 1. 1 is an odd number. 1 cube is still 1, which is still odd, okay? Just plug in like an odd number or even number because it works for everything. It's also odd. What about Q cube? Odd, okay? So what's my contradiction? The Q cube should be even. Why? Why should it be even? You are correct, but why? That's correct, okay? Because, well, PQ squared plus P squared will be odd plus odd. Odd plus odd should be even, but they don't match. This is odd. This should be even. That's a contradiction. Okay. Sorry. Your proof should be definitely you should have more than this. I'll give you 4 solutions so you can have a look. But you definitely should have more than this. But this is a key idea. Okay, so you can do the rest yourself. What about the second case? What's the contradiction here? Anyone? If they're both even, that is correct. Okay, so that's why we need relative prime. Both even, not relatively prime anymore. Okay, so okay, not relatively prime. And the third and fourth cases, you guys can deal with them yourself. Cool. It's similar to case 1. You need to discuss all 4 cases. Okay. Why aren't they? Because if they're both even, they both would have divisor 2. Yes, so not relatively prime anymore. Yeah. Any other question? Anything else? Wait for cool. Okay, so this is a classic type, but also those questions you should know how to do them as well, which I'll give you videos. Okay, watch videos about proof there are no integer or natural solution. Those two are not. They might look similar, but the proof is completely different. Okay, so those questions you have to know how to do them as well, because those are classic questions in this course as well. Okay. Again, I'll send the videos in the Discord channel, and we're gonna move on. Okay, we're gonna move on to induction. Are we clear before we move on to induction? Clear. You're all good. Oh, I'm kind of hungry, but it's like 1 a.m. for me. Yes, that's why we have to cover it. Otherwise, I would go to sleep. It's on the midterm, so I have to cover it. You're all clear. Okay, cool. Induction. I have 40 minutes. Okay, I have to talk about the concept, and I might go over time, but there is nothing I can do. We have to talk about it, okay? Because it's gonna be on the midterm. I'm gonna skip 2. We're not gonna do this one. I wanna do 1 and 3 though. Okay, 3 and 1. I wanna do them. Or maybe one of them. Maybe I will do one of them. I'll record the other one. Maybe tomorrow to not upload it because I'm too sleepy at the moment. I don't think I can do too many questions. So if I don't finish, I'll record. Okay. But eventually you'll get recording for everything. Not example 2 though. Example 2, I don't want to record it. It's way too long. Anyway, I'll give you a solution. Anyway, induction, let's talk about the concept first. The concept is basically domino effect. So if I have a bunch of dominoes, okay, so those are my dominoes. Imagine you have a bunch of dominoes, and imagine I give this one a push. Okay? Then obviously, this one is gonna push the next one, and this one is gonna push the next one, and this one is gonna push the next one, and so on. Right? You guys can imagine that? Why does it work? Okay, why does domino effect work? Why? There are two reasons. One is because I pushed the first one. Right. Two reasons. One is I pushed this one. I'm gonna use an arrow here to tell you that I pushed this one. Okay, that's the first reason I pushed it. The second reason is no matter which one I pick, I push this one, it's gonna cause the next one to fall. Correct? No matter which one I pick. So this one or kth one will cause k plus 1th one. Okay, that's the only two reasons that all of them will fall. Right? Because, well, if I remove any of the condition, if I don't push this one, then none of them will fall. If one of them is gonna be, let's say this one is too far from the next one, maybe I'll move to here. Then I push this one. Well, this will fall here, but this one is not gonna be affected, and you will see that well, my domino is not gonna work. And that's how mathematical strong induction works as well. I need two conditions. I need to push the first one, which is my base case. And I need, no matter which one I pick, the next one will always fall, caused by the previous one. This is my inductive hypothesis. I mean, this is not my inductive hypothesis. Sorry, this is my induction step. Induction. Okay, your hypothesis is this one. Suppose this one's gonna fall, so this is your hypothesis. Okay, so in math, it's exactly the same. I push the first one, which is my base case, and I suppose one of those, it doesn't matter which one, but I suppose one of them will fall, okay? And you prove that, well, this one will cause the next one to fall. Does that make sense? Why induction can give you everything's gonna hold true? It's exactly like dominoes, okay? Make sense? Is this clear? Yeah? Please ask me questions if you have any. Okay, so you should understand it. As I said, if I remove any one of those, it's not gonna work. Okay, if I don't push one of them, obviously none of them will fall. If one is too far away from the next one, it's not gonna cause the next one to fall, then not all of them will fall either. It's exactly the same here. Okay, I need P of 1 to be true, which is I push the first one, and I need, no matter which K I have, P of K implies P of K plus 1. So no matter which one I pick this one or this one or this one or any one of those, that one is going to cause the next one to fall. I need both conditions to say all the statements are true. Okay, so that's why induction works, because I would have P of 1 implies P of 2, P of 2 implies P of 3, P of 3 implies P of 4, and so on. So that's why induction works. Okay, so that's the concept. Now I want to talk about the proof itself. Base case, let me read the base case. You need to check, okay, check does not need to be the first one, okay, does not need to be the first one. It's the smallest one in the set you need to prove, or the smallest one that works, the smallest number that the statement is true. Okay, it does not need to be 1. It can be 2, it can be 10. Okay, it can be 0. It's the smallest number that the statement is true. So what do you need to do? You need to check. So for example, the question says prove something is true for n greater than or equal to 2, or n is natural. Okay, in this case, they ask you to prove for n greater than or equal to 2 where n is natural. then the smallest number that the statement is true will be 2 instead of 1. Okay, I can change this to 10 or 5. If I change this to 5, then your base case is going to be 5. It's the smallest number the statement is true. Or if they say, prove that it works for all natural, then you should think about, well, what's the smallest natural number? 1. That means my base case is 1. Okay, so again, check the smallest number that the statement is true. So you look for what they are asking you to prove. They say, well, prove this is true for all natural number, then all smallest natural number then. Okay, that's the base case. And I want to emphasize the word check. Okay, you don't just assume it's true. You need to prove it's true for the reader. Okay, you need to prove it's true, not suppose it's true. So you need to actually do the proof. Okay, do not start with what you need to prove. Do not start with what you need to prove. Please, okay, do not do that. People keep doing that, and I hate to say it, but you cannot do that. Okay, you can only start with what we know, not what we need to prove. Second, you should have inductive hypothesis, which is you assume, insert whatever you have, what expression you have, but change n to k for and continue for some k in natural number. Keyword some. It's always for some k in natural numbers. Okay, always for some, never for all. So why do they say for any here? Why do they say for any here? Why? Well, we need to prove for any. And how do you prove it? You use one arbitrary element. Okay? Let me write it down. This is what you need to prove. That's why they look different. We need to prove. We need to prove it. And this is what, how do we prove it? We assume. Okay? So let me write the keyword here. We use for some to prove for all. If your assumption, you already assume for any of them, they all always work, then there is nothing for you to prove. You already assume that it works for all. Okay? We use for some to prove for all. Clear? Is this clear what we use for some? Yes, you pick any random. It's because the fact I picked any arbitrary one, that is why it can prove for all. Okay? I didn't pick a specific one that I say, oh, let's pick the 5th one. No, I said, let's pick the kth one, where k is just a random natural number. Does that make sense? So it could be 1, could be 2, could be 3, could be 4, could be anything. But no matter what I pick, the specific k, no matter what I pick, it should always work. That's why you can use for some to prove for all. Okay? Makes sense? Just like how we prove the subsets, we pick one x from a set, but we're actually proving every single element in the set that works. We're still using for some to prove for all. Okay, so your assumption is always for some, never for all. Next is induction. Which really depends on what question it is. Okay, so induction you prove the case for k plus 1, which we'll see. Which we'll see in the example. So I will give you, let's say, 2 minutes to work on the first example. Okay. Less base case and IH doable, but I more want you to focus on how do you prove it. Okay. Of course, you should write base case and IH, but the main focus here is how do you prove it. I'm gonna take it up, and before I take it up, I'm gonna tell you I'm not gonna write the whole thing for example 3, okay? Example 1 is the only one I'm gonna write the whole thing, including base case and IH. So let's read the whole thing properly. So base case, when n equals to 1, you should be able to see base case is 1, right? Because it's for all unnatural, and the smallest natural is 1, so base case is 1. When n equals to 1, I am gonna ask you to do them separately. Okay, so do not do this. Do not do this. We use a different color. So you might want to do this. And that's it. Do not do this. Why? You are not proving it. Okay, it's like you make a statement. You're not proving it. You're not proving it. Okay, so let's do it properly by writing on the left hand side is 3 to the power of 1 plus 2, which is 5. And right hand side, we have 5 to the power of 1, which is also 5. Then we can see clearly left hand side is smaller than or equal to right hand side. So you can put a check mark here. I checked. It's in my base case holds. Okay, and then IH. Now suppose or assume. Okay, you can see that here I said assume expression but change M to K. Expression is this. Okay, this is the expression. So assume 3 to the K plus 2 is less than or equal to 5 to the K. For some K in natural number. Okay, again, for some K in natural. Some K in natural. So now you actually have several different ways to do it. Okay, several different ways. You can start with this side and manipulate it until you get the other side, or you can start with this side, manipulate it until you get the other side. It does not matter. Okay, we don't really care. We don't really care how you want to do it. Let's start with this side for now. Okay, so I'm gonna start with 5 to the n. So now we know that 5 to the power of k plus 1. This is basically 5 times 5 to the k, right? This is 5 times 5 to the k. And remember, I made this assumption to use it. So your induction step always want to use your IH. You always want to use it. So I say, well, I have this, and this is bigger than or equal to this, which means 5 times this should be bigger than or equal to 5 times this. It is clear. So if I multiply by 5 on both sides, should still hold. Does that make sense? It is clear. So I'm gonna say this is bigger than or equal to 5 times 3 to the power of k plus 2. Is this part clear? And this is by IH. Okay, all I did is multiply both sides of the equation by 5. And I have this inequality. It is clear, guys. Yes, okay, nice. So now we can deal with this. And keep remember, okay, this is what I want to prove. I want to prove this. Okay, eventually I want to reach here. You can even write it down. So eventually I want to reach 3 to the power of k plus 1 plus 2. This is my main goal. Okay, so now let's see what this equals to. This equals to 5 times 3 to the k plus 10. Right? And I'm gonna say this is clearly bigger than this. Well, I'm gonna show my step, but can you guys see this term is bigger than this term? Why? This is 3 times 3 to the k. 5 times 3 to the k is clearly bigger than 3 times 3 to the k. 10 is clearly bigger than 2. Does that make sense? Do you guys see how they are actually bigger? Okay, so I'm going to say this is bigger than or equal to 3 times 3 to the power of k plus 2, which equals to what I need to prove. Is this clear for you? You don't need to justify it because it's very clear. Because, well, this is clearly bigger than this. This is clearly bigger than this. Yeah, it's very straightforward here. So no justification is needed here. Okay, is this clear for everyone? So this is this. I'm done. Okay, guys, I'm done. I showed that this is bigger than or equal to this. Okay, as required. What's the difference between the induction hypothesis and induction step? Induction hypothesis is your assumption. Induction step is where you actually do the step. So this is what you assume. And induction step is where you actually prove. No straw induction. So this is your IH. You assume this. Oops. You assume this, which is your IH, and you prove this, which is your induction step. Some people like to call them together as induction. It's up to you. Okay? You can call the whole thing induction as well. Does that make sense? Are we clear on this? And then you can make a final conclusion here. Okay? This is clear. So a lot of people, they really don't like inequality because, well, you just need to keep finding the smaller and smaller expression, basically, or bigger expression. You don't have to make them equal. Just like how I got here. They clearly don't equal to each other, but I don't need them to be equal. I just need to find something smaller. On the next quiz, I have no idea. We're too far away from the next quiz. Maybe not. I really don't know. Okay, this is clear, right? We're good? I need to make sure everyone understands what's going on. Because induction should be 3 marks for you. So my expectation is everyone get perfect. Everything's good? Any question at all? Can I move on? Okay, nobody said anything. I'm gonna move on, okay? We're gonna do question 3. Question 2 is not as important. Question 3 is another classic one. The divisibility questions are important as well. Okay? You need to know how to do them. This one I'm not gonna write the whole thing. Base case, clearly, 1 equals to 1. Okay? You can check it yourself. You can plug in 1 and see if it's divisible by 18. That's your thing. Then we suppose 4 to the k plus 6k minus 10 is divisible by 18. It's the same as equals to 18, let's say m. Okay, for some k in natural and for some m in integer. Okay? Divisible by a number means that it's a multiple of this number, so you can do that. It's gonna make your life easier. That's why I'm doing this. That's your IH. And then, oh, I'm so hungry. Sorry. And then I need to show 4 to the power of k plus 1 plus 6 times k plus 1 minus 10. I want to show this expression is divisible by 18. Okay? That's what I need to do. And to do this, it's actually always the same. There's not much difference. To do this, guys, I expand it first. I write it as 4 times 4 to the k plus 6k plus 6 minus 10. When you have such question, please do not combine terms together. For example, those two terms, I know we can merge them together, but please do not do that. Okay? Don't write it as a minus 4. We don't want to do that. Why? Because we want to use our IH. Okay? I want to use this. In other words, I need to find those terms in my new thing. Okay? So you can see that. I have this. I have 6k. But I have 4 copies of 4k, 4 to the power of k. So this 4 copies is my problem. This 4 is my problem. It's problem. Okay, so this is my problem. There are 2 ways to deal with it. Okay? One way is you can write it as 1 plus 3 and use distribution. Then you have a 4 to the power of k. Combine with the other terms, maybe it's gonna work, but maybe not. Okay, you can give it a try. You'll see that it's not gonna work. So I'm gonna talk about the second way that works, which is instead of writing this, how? I'm gonna do because this is 4 copies, right? This is 4 copies of 4 to the k. This has 4 copies. Those have only 1 copy. I want to use this. Why not just make everything 4 copies and minus the extra terms? Which means, well, I'm gonna make it 4 times 4 to the k plus 6k minus 10. Now I made everything 4 copies. Okay, so now this has 4 copies. This also has 4 copies. This also has 4 copies. But now, because of that, they don't equal to each other anymore, which means I need to minus the extra terms. Okay? First of all, I need to plus 6 because, well, in here, I have to plus 6. So let me do highlighting again. So this have to come here, right? And then this is down. Thus and thus, they are the same. But the other terms are not the same. So here I have 4 times 6k. Here I have 6k. I have 3 extra copies, so I need to minus 3 extra copies. And similarly, here I have minus 10. I have 4 copies of minus 10. Right, 4 copies of minus 10, which means I cannot do that. I have to add them back, basically. So I need to add 3 times 10. Add the 3 copies back because I subtract 3 more copies of 10. Does this make sense to everyone? Does this make sense to everyone? Yes, yes? I'll give you some time to digest this, okay? Again, let me repeat because I know some of you might not get it, but it's important to understand what's going on, okay? So again, I look at this and I know I need to use my IH. However, after comparison, I see that, well, I have 6k, I have minus 10, but the 4 to the power of k has 4 times it, has 4 copies, which means I cannot use this directly. We could, okay, we could. It's just in this question it does not work. So using this method works more than the other method. I said you can do 3 plus 1, but 3 plus 1 way does not always work. This works in more different questions. So I'm teaching you the one that's more general, okay? But in a lot of questions, you can do that. Okay, repeat, let me go back to this. Because this one has 4 copies, I cannot use this directly, so I'm gonna make everything 4 copies so that I can use it. So I'm gonna have 4 times this, which equals to 4 times 18m, right? And then I subtract the extras I added. So because, well, here I added 3 more copies of 6k, so let me subtract them. Here I subtract 3 more copies of 10, so let me add them back. So that this 2 lines are actually equal to each other. Once I do that, you'll see this question is much easier because I have 4 times 18m. This is by h. And then now you can merge things together. So you have minus 18k and then plus 36. And now you can see, well, I can factor out 18, which is 18 times 4m minus k plus 2. Right? And this is clearly divisible by 18. Oh, by the way, this you should say by h. Does this make sense? Yes? No? So this is a key step. You have to understand what's going on. Okay, so from here to here, this is a key step. First line to second line is a key step. Is this clear for everyone? Then give me some feedback, guys. Some feedback. Yes or no? Is this clear? Or, okay, so we're done. Okay? The rest you make a conclusion, because this basically shows that it's divisible by 18. And you're good. The 3 step. Wait, 3 step? You mean here? You mean this? Is this what you're talking about? Third step. This step. Okay, so 4 is from here. Thus, we make the assumption that it's 18m. Okay? And then minus 18k from here. And then 30 plus 6 is 36. Yes, that's all I did. I merged some terms together. Any other question? Are you good? You're all good? All good? All good? Question 2. Did you guys learn partial fraction in 136? Are you guys there yet? Partial fraction? Yes. Recently? Okay. Now you can do this. Hint is partial fraction. That's my hint. Okay? So hint is partial fraction. Oops, fraction. In other words, you need to write it. You can see that as you can factor something out. You can write it as something something minus another fraction. Okay, one fraction minus another fraction. And you expand you'll see all the middle terms cancel out, and then you reach one thing. We don't do this tutorial because, well, you will not be tested in this midterm. Okay, so after midterm, go ahead and give it a try. Just, it's a good practice for 136 as well. But before midterm, don't worry about it. Okay? Yes, that's what I'm saying. Before midterm, don't worry about it. After midterm, you can give it a try. Cool? Are we good, guys? Can I go to sleep? I'll send you the practice questions in the channel, and I'll create a channel, and you can have a look at there. But I'm gonna stop here because I still need to go shower. Let's go sleep. You're welcome. And let's enjoy the rest of your day. Good night.